There are two kinds of silence in the universe. The first is the silence of absence, the cold, indifferent quiet of the void between worlds, a vast emptiness that has never known a thought or a breath. It is the default state of the cosmos, the background hum of utter neutrality against which all of existence plays out. But there is another silence, a far more profound and unsettling one. It is the silence of a secret being kept. It is the quiet of a place that once knew sound, the hush of a world holding its breath waiting for a question to be asked. For all of human history, we have stood on our small noisy world, shouting that one defining question into the great dark expanse, are we alone? We have woven the answer into our myths, painted it onto our ceilings, and launched it into the heavens on plaques of gold. The question is not a product of science, but its genesis. It is the primal curiosity that predates telescopes and rocketry, a deep instinctual need to know our own context, to understand if the miracle of life on Earth is a singular lonely flame or merely one spark in a cosmic bonfire. We have turned our gaze outward, scanning the star fields for a whisper, a signal, a sign that we share the universe with another intelligence. Yet perhaps the answer we seek has never been in the distant glimmer of a far-off star system. Perhaps it has been waiting patiently next door, hiding in plain sight. It has been our constant celestial companion, a ruby-red ember in the twilight sky, a world that has haunted our imaginations for millennia. Mars. The name itself echoes with conflict and mystery, a place so tantalizingly similar to our own, yet so devastatingly different. It is the planet that serves as the ultimate cosmic mirror, reflecting back at us not only our hopes for companionship, but also our deepest fears of extinction. We look at its wind-scoured plains and desiccated riverbeds and we see a ghost of a world that might have been. A ghost of a world that in some ways our own Earth could one day become. The early astronomers, peering through their brass and glass instruments, were so desperate for a connection that their minds filled in the blanks. They saw canals, great feats of engineering they believed were carved by a dying civilization, a desperate attempt to channel water from the polar caps to their parched cities. They were wrong, of course. There were no canals, no Martians of the kind they imagined. But their error was not one of science. It was one of profound, beautiful, and utterly human hope. They were right to sense that Mars was a place of profound stories of planetary-scale drama. They just had the timeline wrong. The story of Martian life, if it exists at all, is not one of a contemporary civilization, but an ancient epic written in the language of geology and chemistry, a tale of a world that had its chance and lost it. To understand the Mars we see today, a freeze-dried, radiation-bombed desert, we must first travel back in time, back more than 3.5 billion years. In this distant epoch, the sun was younger and dimmer, but Mars was vibrant. It was not red, but blue. Imagine standing on a Martian shore beneath a sky thicker and paler than the one we know today. You would hear the rush of wind and the lapping of water. You would see clouds scudding across the sky, casting shadows on a landscape carved by flowing rivers that snake their way across continents, pooling into vast lakes and possibly even a shallow northern ocean. This ancient Mars was a world of possibilities. It possessed all the known ingredients for life as we understand it. It had liquid water, the universal solvent in which the chemistry of biology can unfold. It had a source of energy from the young sun and from the planet's own internal volcanic heat, and it had the essential organic building blocks, carbon-based molecules, delivered by the rain of comets and asteroids that was a constant feature of the early solar system. For hundreds of millions of years, Mars was a habitable world. It was a cradle, a planetary-scale laboratory where the grand experiment of life could have begun, entirely separate from the one taking place on its sister world Earth. Here in the shallow, sunlit waters of a Martian lake, the intricate dance of molecules could have sparked into something more. Something that could replicate, that could metabolize, that could be called by any definition alive. This is not science fiction. This is the story that the Martian rocks themselves are telling us. But every great story has a tragedy at its heart, and the tragedy of Mars is one of the most profound we have ever discovered. Something went terribly wrong. Deep within the planet's core, the churning dynamo of liquid iron that generated its global magnetic field began to falter. This invisible shield, this planetary guardian, had been protecting the fragile atmosphere from the sun's relentless wrath, a constant stream of charged particles called the solar wind. As the dynamo sputtered and died, Mars was left defenceless. The solar wind, like a celestial blowtorch, descended upon the planet and began to strip its atmosphere away molecule by molecule over millions of years. The air thinned, the pressure dropped, and the planet grew cold. The water that had once flowed freely across its surface either boiled away into space or froze solid, locked away in the polar caps and buried deep underground. The world that was once blue and alive was relentlessly scoured, sterilized by unfiltered solar and cosmic radiation, and painted the colour of rust. The age of water was over. The age of silence had begun. Yet a memory of that watery past survives. If life did get a foothold on that ancient blue Mars, where would we look for its remains? Where would you search for a fossil, not of a dinosaur, but of a microbe? You would go to a place where water once pooled, where fine sediments gently drifted down and settled on the bottom of a lake layer by layer, entombing any microscopic organisms that lived and died there. You would search for a place that could have acted as a perfect natural preservative, a geological time capsule sealed for billions of years. You would go to a place like Jezero Crater. This 45-kilometre wide impact basin is not just another crater on a planet covered in them. Seen from orbit, it is an astonishingly clear portrait of a watery past. On its western rim, you can see the unmistakable phantom-like scar of a river channel that breached the crater wall, and fanning out from that breach is a feature that makes the hearts of astrobiologists race a perfectly preserved river delta. It is a fossilized fingerprint of flowing water, a place where a mighty river slowed, depositing layers of clay and carbonate minerals, the very kinds of materials that on Earth are exceptionally good at preserving the delicate traces of ancient life. To send a mission here was an act of supreme scientific audacity. It required the most sophisticated robotic explorer ever built a machine designed not just to be a geologist, but a forensic investigator, an astrobiologist on 6 wheels. Its name is Perseverance. It is the culmination of decades of Martian exploration, the sharpest tool we have ever sent to another world, carrying a payload of instruments so sensitive they can detect the chemical composition of a single grain of dust. On February 18, 2021, after a 7-month journey across interplanetary space, Perseverance arrived at Mars. But arriving is the easy part. It then had to perform the single most complex and dangerous maneuver ever attempted in robotic exploration: the entry, descent and landing. Plunging into the thin Martian atmosphere at over 12,000 miles per hour, its heat shield glowing hotter than lava, it had to slow itself down in what engineers call the 7 minutes of terror. It was a perfectly choreographed ballet of parachutes, rockets, and a jet-powered sky crane that lowered the 2,000-pound rover onto the surface, with pinpoint precision landing it right on the floor of the ancient lake bed it had travelled 300 million miles to explore. For us sitting here on Earth, those 7 minutes were an agony of waiting. We could only watch the telemetry holding our collective breath as a machine acting on its own. Intelligence negotiated a life-or-death challenge. When the first signal of a safe landing arrived, it was more than a technical victory. It was a moment of profound connection. We had done it. We had placed our most capable emissary at the most promising location we have ever found in the search for life beyond Earth. And now the true mission could begin. Perseverance is not like its predecessors. While rovers like Spirit, Opportunity and Curiosity were designed to follow the water, to read the geological history of Mars, Perseverance was designed to do something more. Its primary objective is to seek the signs of ancient life itself, what scientists call biosignatures. With a suite of powerful tools, it systematically interrogates the rocks of Jezero. An instrument named Pixel uses a hair-thin X-ray beam to map the elemental composition of a target, revealing its fine-scale chemistry. Its partners, Sherlock and Watson, use ultraviolet lasers and cameras to hunt for the kinds of organic molecules and mineral patterns that life tends to leave behind. The rover is a tireless field scientist crawling across the delta, analysing rock formations that were once mudstones at the bottom of a lake or boulders washed down in an ancient flood. Every day its human team back on Earth pores over the data, debating which rock holds the most promise, which target is most likely to contain a clue to Mars's biological history. They are searching for the faintest of whispers, the most subtle of hints. They do not expect to find a fossilized bone. They are looking for microscopic textures in the rock, for clusters of organic compounds that are difficult to explain through geology alone for the chemical ghost of a metabolism that ceased billions of years ago. But here is the most critical and revolutionary part of its mission. Perseverance cannot and was not designed to provide the final definitive proof of life. The instruments required for that kind of unambiguous analysis are too large, too complex, and too power-hungry to send to another planet. No, the rover's ultimate purpose is not to be a laboratory but a curator. It is a collector. Aboard Perseverance is a carousel of 43 pristine, meticulously sterilized titanium tubes. When the rover's instruments identify a rock of special interest, a sample so compelling it could rewrite our textbooks, it extends its 2-meter-long robotic arm. With a coring drill at the end, it carefully cuts out a piece of the Martian rock, a sample about the size of a piece of chalk. It then seals this precious geological core inside one of the titanium tubes, creating a perfect hermetically sealed time capsule. This is the biosample. It is the most valuable and carefully selected piece of alien real estate in human history. The rover then either stores the tube aboard its chassis or deposits it on the Martian surface at a designated collection point, creating a cache of discoveries for a future mission to retrieve. And this is where the story elevates from a mission of exploration to a saga of epic proportions. Collecting the samples is only the first act in an audacious multi-part multi-spacecraft plan known as Mars Sample Return. This is a mission so complex, so ambitious, it feels like it belongs in a far future science fiction novel. It will require a second lander to touch down near the sample cache. This lander will deploy a smaller fetch rover that will scurry across the surface, locating and collecting the tubes left by Perseverance. It will then return to the lander and load them into a small rocket, the Mars Ascent Vehicle. This will be the first rocket ever to launch from the surface of another planet. It will blast off from Mars, carrying its priceless cargo into orbit. But it cannot get all the way back to Earth on its own. Waiting in orbit will be a third spacecraft and orbiter built by the European Space Agency, which will have to perform an equally astonishing feat. It must autonomously rendezvous with and capture the basketball-sized sample container as it hurtles through the Martian orbital environment. Once the transfer is complete, the orbiter will fire its own engines and begin the long journey home, a celestial courier carrying the most anticipated delivery in the history of science. Years from now, a capsule will streak through Earth's atmosphere and parachute down into the Utah desert. Inside will be the pristine, untouched soil and rock of Jezero Crater. For the first time, we will hold in our hands pieces of another world that we have chosen, that we have curated, that we have brought home. These samples will be analysed in the most advanced laboratories on the planet, scrutinised by scientists with instruments far more powerful than any we could send to Mars. They will be able to search for evidence of life with a level of certainty that is simply impossible to achieve from millions of miles away. And so we are brought back to that most profound of questions, the one that has driven this entire multi-decade, multi-billion-dollar endeavour. The question is no longer an abstract philosophical musing shouted into the void. It has been refined, focused, and sealed inside a titanium tube lying in the red dust of Mars. What if one of those samples, a carefully chosen biosample, contains the answer? What if under the beam of an electron microscope or within the chamber of a mass spectrometer we find it? The evidence might be subtle. It might be the fossilized microscopic form of a single-celled organism, an alien bacterium frozen in time. It could be a complex organic molecule that by all the laws of chemistry could not have been formed by geological processes alone. Or in the most stunning possibility of all, it might be something more. In the protected subsurface away from the harsh radiation, perhaps life on Mars never truly died. Perhaps it merely retreated, entering a state of dormancy, a deep hibernation waiting for conditions to improve. What if, when we place a grain of that Martian soil in a nutrient-rich medium here on Earth, something begins to stir? What if we discover that Mars was not just alive in the distant past, but that in some microscopic, tenacious form it is still alive today? We stand on the precipice of a discovery that would forever alter our understanding of our place in the universe. The samples are there. The technology to bring them home is being built. The silence of Mars is about to be broken, and we are about to learn if it is the silence of absence or the silence of a world that has been keeping the greatest secret in the solar system. Before we ever sent a single rivet of metal or a solitary watt of power towards Mars, we had already travelled there countless times. We went in our minds, carried on the fragile vessel of the human imagination. For centuries it was simply a baleful wandering star, a crimson smear against the velvet black, the embodiment of a war of fire of endings. But through the polished lenses of our first telescopes, that point of light resolved itself into a disk, a world, a place. And with that transformation, a new story began to unfold, not one of the endings, but of tantalizing possibilities. You have to understand the power of that moment. In the late 19th century, an astronomer named Percival Lowell, a man of wealth and unshakable conviction, peered through the clear Arizona air and saw not just a world, but a civilization. He saw a planet dying of thirst, and a brilliant ancient race of engineers crisscrossing its surface with a magnificent network of canals, funneling water from the polar ice caps to their parched equatorial cities. He drew what he saw, mapping these intricate, impossibly straight lines with a meticulous hand. These were not the meandering, chaotic patterns of nature. They were the unmistakable signature of intelligence. His maps and books captured the world's imagination, creating a Mars that was a mirror to our own world, a place of grand achievements, of desperate struggles of life. It was a planetary romance, a breathtaking vision of cosmic neighbours. Scientists of his time were skeptical, rightly pointing out that the human eye, strained at the very limit of its perception, has a tendency to connect disparate dots into coherent lines. They argued that these canals were optical illusions, phantoms born of desire. And they were right. Lowell's canals were not there, but their absence on the planet did nothing to erase them from our collective consciousness. They became the foundational myth of Mars, the grand what-if that would propel us across the void. The dream of Lowell's dying noble civilization was so powerful, so deeply intoxicating, that we simply had to go and see for ourselves. We had to know. That journey began not with a roar, but with a whisper, a stream of digital data trickling across 134 million miles of emptiness. In 1965, a little robotic probe named Mariner 4, a spindly thing of solar panels and ambition, executed the first successful flyby of Mars. In mission control, scientists who had grown up on stories of Martian princesses and canal builders leaned forward, waiting for the first close-up photographs of another planet in human history. The images, painstakingly assembled line by line from a faint radio signal, began to form, and with each one the beautiful dream of Percival Lowell was systematically, brutally dismantled. There were no canals, no cities, no signs of a planet-spanning engineering project. There was only rock and dust and silence. The photographs revealed a surface that looked disturbingly familiar, but not like Earth. It looked like the moon. Crater after crater pocked a desolate, barren landscape. It was a surface that appeared to have been battered frozen and left for dead billions of years ago. The atmosphere was found to be devastatingly thin, a mere ghost of a breath offering no protection from the sterilizing bath of cosmic radiation. Mars wasn't a dying world. The first evidence suggested it was already long dead, a cosmic fossil. The deflation was palpable, a quiet heartbreak felt through the scientific community. The vibrant living Mars of our imagination had been replaced by a cold, cratered tombstone. For a decade, this was the prevailing image. Yet the question of a life once asked is not so easily dismissed. It lingers, it gnaws. A flyby photograph, no matter how revealing, cannot see everything. It cannot scratch the surface, taste the soil, or breathe the air. To truly hunt for life, we had to do more than just look. We had to go there. We had to land. And so in the mid-1970s, NASA embarked on one of the most audacious and ambitious missions ever conceived. They would send two identical landers named Viking 1 and Viking 2 on a half-billion-mile journey to the Red Planet. These were not mere geological surveyors. They were robotic, automated extraterrestrial biologists. Each lander carried a miniature laboratory, a 3-part experiment designed to answer, once and for all, that profound, lingering question: is there life on Mars today? You have to appreciate the sheer audacity of this gamble. We were reaching across the solar system with a robotic hand, scooping up a handful of alien dirt and feeding it. It was the ultimate test. Imagine the scene on July 20th, 1976. 7 years to the day after humanity first walked on the moon, the Viking 1 lander settled onto the golden plains of Cruiser Planitia. Its camera whirred to life, revealing a panorama of rust-coloured sand and pink sky, a landscape of sublime alien beauty. But the real work was about to begin inside the lander's gleaming white chassis. The robotic arm, in a moment of historic significance, extended, dug its tiny shovel into the Martian soil, and retracted, delivering the first ever sample of another world into its onboard laboratory. 3 separate experiments each, a different trap for Martian microbes, awaited the precious dust. The first, called the gas exchange experiment, essentially added water and a nutrient-rich broth, a sort of chicken soup for microbes to the soil, then watched to see if any gases like oxygen or carbon dioxide were released, the telltale signs of respiration or metabolism. The second, the pyrolytic release, took a different approach. It replaced the Martian air in the test chamber with a radioactive form of carbon dioxide, gave the soil sample some light and time to photosynthesize, then baked it to see if any of that radioactive carbon had been incorporated into organic matter, a sign of alien plant-like life. But it was the third experiment that held the most promise, the one that had everyone on the edge of their seats. It was called the labelled release experiment, a beautifully clever design by scientist Gilbert Levin. The concept was simple and elegant. It would feed the soil a drop of water containing simple organic nutrients, all of which were tagged with radioactive carbon-14. The theory was that if any microorganisms were present in the soil, they would consume these nutrients and, just like us, would exhale waste gas. This exhaled gas containing the radioactive carbon-14 would then be detected by a sensitive radiation counter. It was a direct, unambiguous test for active metabolism. Any result other than a flat line would be a monumental discovery. Back on Earth, the data began to stream in from the labelled release experiment. At first there was nothing, just the baseline reading of background radiation. The line on the graph was flat. Then it happened. The line began to climb, slowly at first, then more steeply. Radioactive gas was being released from the soil. It was exactly the curve they had predicted. It was exactly what you would expect to see if you ran the same experiment on a sample of life-filled soil from your own backyard. In the laboratories of the Jet Propulsion Laboratory, a quiet, stunned excitement grew. Could it be? Had they actually found it? The experiment was repeated. The same result. They ran a crucial control test. They took another sample of soil, heated it to a sterilizing temperature to kill any potential life, and then ran the experiment again. This time, the line on the graph stayed flat. The nutrient was not consumed. The gas was not released. This was the smoking gun. It behaved precisely like a biological signature. Champagne was put on ice. Press conferences were tentatively planned. For a few tantalizing days and weeks, it seemed humanity was on the verge of its most profound discovery, that we are not alone. The universe, it seemed, was alive. But science demands more than one witness. And as the data from the other 2 experiments came in, the beautiful, simple story began to crumble into a maddening puzzle. The gas exchange experiment did see a release of oxygen, but it happened instantly, a sudden puff the moment water was added, suggesting a purely chemical reaction, not a slow biological process. And the pyrolytic release experiment looking for photosynthesis came back stubbornly negative. The fatal blow, however, came from a different instrument on the lander altogether, a device called the Gas Chromatograph Mass Spectrometer, or GCMS. Its job was to bake the soil and sniff for the presence of organic molecules, the fundamental building blocks of life as we know it. The GCMS was incredibly sensitive. It could detect organic compounds at a level of parts per billion. It heated the soil, analysed the vapours, and found nothing. Absolutely nothing. Not a single definitive trace of an organic molecule, and with that the dream collapsed. How could this be? How could you have active metabolizing life as the labelled release suggested, but not a single organic molecule from the bodies of those microbes, living or dead? It was like finding a warm, breathing body that was somehow made of pure inorganic sand. It made no sense. It was a paradox that split the scientific community down the middle. One camp led by the steadfast Gilbert Levin has argued for decades that Viking did find life, and that the other instruments were simply not sensitive or designed correctly to confirm it. The other much larger camp concluded that some unknown exotic chemistry must be at play in the Martian soil. They theorized that powerful oxidants like peroxides created by the ultraviolet radiation bombarding. The thin atmosphere had not only destroyed any organic molecules on the surface, but had also reacted violently with the water in the labelled release experiment mimicking a biological signal, a false positive. This contradiction became the central ghost in the machine of Mars exploration. For nearly 20 years, the ambiguity of the Viking results led to a long Martian winter. We had asked the ultimate question, and in return the universe had given us a riddle wrapped in an enigma. It was a scientific dead end. The problem a new generation of scientists began to realise wasn't necessarily with the experiments themselves. The problem was that we'd tried to run before we could walk. We had searched for the inhabitants of a house before we had even confirmed the house was habitable. A fundamental paradigm shift was needed. We had to stop looking for Martians and start looking for their home. The question had to change. It was no longer, is there life on Mars now? It became, was Mars ever a world that could have supported life? This was a geological question, not a biological one. It was a search for past environments for the one ingredient that on Earth is synonymous with life-liquid water. And so began the Great Martian Renaissance. We launched a fleet of new explorers, not as biologists but as robotic geologists sent to be our eyes and hands on a planetary crime scene. We sent orbiters that could see in wavelengths of light invisible to the human eye, mapping the mineral composition of the entire planet from above. We sent landers, and for the first time intrepid rovers designed to follow that one simple, powerful mantra, follow the water. In 1997, the tiny Sojourner rover part of the Pathfinder mission trundled off its lander and analysed rocks that suggested they had been shaped by immense ancient floods. Then came the true marathon runners, the twin rovers Spirit and Opportunity, who landed in 2004 for a 90-day mission and ended up exploring for years. Opportunity landed in a small crater, and in one of the great serendipitous moments of exploration, found itself staring at an outcrop of layered bedrock. Within that rock, it found tiny spherical concretions of the mineral hematite nicknamed blueberries. On Earth, these formations almost always form in the presence of liquid water. Opportunity had landed in what was once the muddy bottom of a salty sea or lake. It was the first definitive proof of a standing body of liquid water on ancient Mars. The evidence began to pour in from every mission. Orbiters mapped the ghost shorelines of a vast, long-vanished northern ocean. They saw the dendritic branching patterns of the ancient river valleys so achingly familiar carved into the oldest highlands. They found clay minerals and sulfates deposits that are chemical fingerprints left behind by water, interacting with rock over immense periods of time. Then, in 2012, the Curiosity rover, a car-sized mobile laboratory, landed in Gale Crater. It soon discovered the beautifully preserved remains of an ancient stream bed, with smooth rounded pebbles that could only have been tumbled and shaped by a briskly flowing river. Analysing the rocks, Curiosity found all the key chemical ingredients necessary for life: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, in a freshwater environment with a neutral pH. This was not a toxic, acidic brine. This was water you could drink. The picture that emerged was astonishing, a complete rewriting of our understanding of Mars. The cold, dead, moon-like world of the Mariner photographs was just a mask. Beneath it lay the ghost of another planet entirely. A young Mars with a thicker atmosphere with blue skies and white clouds. A Mars where rain fell and rivers flowed into vast lakes and shallow seas. It was a warm, wet, and chemically rich world. For 1 billion years, perhaps longer, Mars was by every definition we have a habitable planet. The dream of Percival Lowell, it turns out, was not entirely wrong. He was mistaken about the canals and the engineers a victim of his own hope, but his core intuition that Mars was once a world more like our own, a place where life could potentially take hold, has been spectacularly vindicated by a century of science. The frustrating enigma of the Viking experiments taught us a crucial lesson: you cannot hope to find a needle in a haystack without first understanding the nature of the hay. We have now spent decades understanding that ancient Martian landscape. We have followed the water to its ancient sources. We have confirmed beyond any reasonable doubt that the conditions for life were once there. And so with that hard-won knowledge as our foundation, the old question can finally be asked again, but in a new and far more powerful way. Not, is there life? But is there any evidence of that past life still preserved? We now know exactly where to look in the mudstones of an ancient river delta, where the whispers of a 3.5 billion-year-old biosphere might still be locked away in stone. The time for asking if Mars was habitable is over. The time has come to collect the evidence, and so after the fire and the fury of entry comes the silence, a profound quiet that has reigned over this place for 3 billion years now, broken only by the faint hum of electronics and the whisper of a thin carbon dioxide wind. Through the eyes of perseverance we see our new home. We are in Jezero Crater, but this is no mere impact basin. Before you lies the skeletal ghost of a world that might have been. A vast dry lake bed cradled by a crater rim that rises like the shore of a forgotten ocean. And there etched into the landscape is the undeniable fossil of a river delta, a fan of sediment and stone carved by water that flowed splashed and pooled here in a time before memory. This was a place of powerful currents and gentle ponds, a place of mud and sand where the chemistry of a young wet Mars could have performed its most profound experiments. It was chosen from over 60 candidate locations, not for what it is, but for what it was. We have not sent our most advanced robotic explorer to a random patch of Martian dust. We have sent it to a crime scene where the prime suspect, a life-giving liquid water, has long since vanished, leaving behind only the most tantalizing of clues. We are here to read the rings of its memory, to sift through the sediment of its history, and to ask the stone itself for its testimony. Every grain of sand, every layered rock is a potential page in a story we are only just beginning to comprehend. The air is cold, the pressure less than 1% of Earth's, the radiation relentless. By all accounts, this is a dead world. But here in this specific hallowed ground, the ghosts of a living one feel unnervingly close. To explore this sprawling 4 billion-year-old museum, you cannot simply drive. You must think. The distance to Mars means a radio signal travelling at the speed of light takes over 20 minutes to make a round trip. Real-time control is an impossibility. A human operator with a joystick would be a liability, a surefire way to drive this $2 billion prodigy off a cliff or into a sand trap. No Perseverance must forge its own path. It carries a second brain and intelligence dedicated solely to the art of survival and navigation. We call it AutoNav, but that simple name belies the breathtaking complexity of its function. It is in essence a robotic field geologist with an innate sense of self-preservation. As it prepares to move, its twin navigation cameras mounted on the mast snap a stereoscopic image of the terrain ahead. From these two slightly different perspectives, its processors construct a three-dimensional map of the world in front of it, a virtual landscape of rock slopes and hazards rendered in mathematical precision inside its mind. It identifies every potential threat, a rock that is too sharp a slope, that is too steep a patch of sand that could swallow its wheels. Then, the rover's main computer, the thinking part of its brain, plots dozens of potential routes through this virtual minefield, weighing the safety distance and energy cost of each path. It doesn't just see a rock. It calculates its volume, assesses its stability, and charts a course around it with margins of error measured in centimetres. After selecting the optimal path, it drives for a few meters, then stops. It erases the old map and builds a new one of the fresh terrain that has come into view. Think drive, stop. Think drive, stop. A meticulous and patient rhythm of exploration that allows it to safely traverse this alien wilderness entirely on its own. This is not a pre-programmed toy following a line on a map. This is a machine making its own decisions moment by moment on the surface of another world. It is the closest we have ever come to instilling a machine with a human explorer's instinct, a cautious curiosity that pushes it ever deeper into the unknown, while constantly looking over its shoulder. This remarkable autonomy frees the human science team on Earth from the tedious task of micromanaging every wheel rotation. They can focus on the grander questions, pointing to a distant ridge and saying, "Go there," trusting the rover to find its own way to be the master of its own journey across the floor of this ancient lake. But navigation is only the beginning. To truly understand Jezero Perseverance is equipped with a suite of instruments so advanced they represent a quantum leap in planetary science. This is not just a vehicle, it is a rolling autonomous laboratory of unparalleled sophistication. Its sensors are far more powerful, more perceptive than our own. On its mast, standing nearly 7 feet tall, is the head of the beast. Here we find Mastcam Z its primary eyes. The Z stands for zoom, a powerful lens that can reveal details as small as a housefly from the length of a football field. But its true power lies not just in seeing, but in seeing the invisible. It can perceive the world in a spectrum of colours far beyond human vision, into the infrared, allowing geologists back on Earth to make preliminary identifications of minerals based on how they reflect sunlight. It's like having a superpower that reveals the hidden composition of the landscape painting the crater floor in a palette of scientific truth guiding the team toward the most promising targets. Alongside these cameras is an instrument that feels like it's been pulled from the pages of science fiction supercam. It is a geologist's dream tool, a 5-in-1 package of extraordinary power. Its centerpiece is a powerful infrared laser, a celestial blowtorch capable of firing a pulse of energy at a target up to 20 feet away. In less than a billionth of a second, this laser blast vaporizes a tiny pinprick of rock, heating it to 10,000 degrees and creating a flash of plasma, a miniature star on the Martian surface. A built-in telescope captures the light from this spark and a trio of spectrometers analyzes it, breaking it down into its constituent wavelengths. Each element, whether iron, silicon, potassium or carbon, burns with a unique and identifiable color signature. From a single flash of light, we can determine the precise elemental chemistry of a rock. From a distance, a chemical scream across the Martian air that tells us its fundamental nature. Supercam also carries a microphone, the first of its kind to be used scientifically on the surface of Mars. When the laser strikes, the rapid expansion of vaporized rock creates a shock wave, a tiny pop that travels through the thin atmosphere. By listening to the intensity of that sound, scientists can infer the hardness and physical properties of the rock, distinguishing between a dense water-altered stone and a softer, more porous one. For the first time, we are not just seeing Mars or tasting its chemistry. We are hearing it. We are listening to the whispers of its geology, a symphony of data conducted by a laser beam. This ability to survey from afar is revolutionary. It allows the rover to act as its own reconnaissance scout, rapidly assessing dozens of potential targets without having to drive to each one, saving precious time and energy for only the most scientifically compelling candidates. It's the first pass, the Grand Survey, that filters the entire landscape down to a handful of rocks worthy of a more intimate inspection. Once a target is chosen, the rover's most powerful tools are brought to bear, and these reside at the end of its 7-foot robotic arm. This arm is a marvel of dexterity, capable of positioning its instruments with sub-millimeter precision. Here we find the detectives of our story, the instruments that get up close and personal. One of these is PXL, the planetary instrument for X-ray lithochemistry. PXL is the master of elemental detail. It fires a hair-thin beam of X-rays at the rock, causing the atoms within to fluoresce, to glow with their own X-ray light. Each element gives off a characteristic energy signature, and PXL's detector maps these signatures with microscopic accuracy. It doesn't just tell us what a rock is made of, it shows us how it is made, revealing the distribution of elements grain by grain. We can see how crystals formed, how water deposited different minerals in fine layers, how the chemical environment shifted over eons. It's like being able to read the individual words and sentences on a page, not just the title of the chapter. Pixel provides the deep context, the fine-grained evidence of the world in which this rock was born, and alongside it, searching for an even more profound secret, is Sherlock. Its name is an homage to the world's greatest fictional detective, and its mission is every bit as challenging, to search for the building blocks of life itself. Sherlock uses an ultraviolet laser to scan the rock's surface. Certain minerals, and most importantly organic molecules, absorb this UV light and re-emit it at a lower energy, a phenomenon called fluorescence. Just as a black light can reveal hidden stains on a carpet, Sherlock's laser is designed to make organic compounds, the complex carbon-based molecules that form the basis of all known life, light up against the dark, inorganic background of the rock. It is our primary tool in the search for biosignatures. Accompanying it is its trusty partner Watson, a high-resolution camera that acts as a geologic hand lens taking incredibly detailed close-up images of rock textures, structures, and any fluorescing spots that Sherlock detects. Together, Sherlock and Watson are the ultimate team scanning for the faintest chemical residues that might have been left behind by ancient Martian microbes. They are hunting for the molecular ghosts of Jezero. The process is a masterpiece of scientific patience. After months of surveying with Mastcam-Z and Supercam, the team identifies a truly special rock formation, a fine-grained sedimentary layer they nickname the Mortier Formation. The rock here appears to be volcanic in origin, but has clearly been altered, sculpted, and reshaped by the persistent presence of water. This is the perfect place to begin the search. AutoNav guides Perseverance on a careful multi-day drive to the chosen location. The arm with its 100-pound turret of instruments unstows with surgical grace. But we cannot simply analyse the surface. For billions of years, this rock has been exposed to the harsh Martian environment, bombarded by cosmic rays and solar radiation that would destroy any delicate organic molecules near the surface. We must look deeper. The arm first brings forth the Gaseous Dust Removal Tool, or GDRT, which puffs out nitrogen gas to blow away loose dust, giving us our first clean look. Then comes a different tool, the abrading bit. It is a robotic grinder tipped with diamond cutters which spins against the rock face. For hours it meticulously scrapes away the top few millimeters of weathered irradiated rind. This act is one of the most crucial of the entire mission. We are peeling back the skin of the modern dead Mars to reveal a pristine protected surface beneath a window into the ancient world untouched for eons. The circular patch it creates, just 2 inches in diameter, is a fresh wound on the stone, and it is here in this raw exposed material that the truth might lie. The arm retracts, then repositions itself, placing Pixel and Sherlock over the abraded patch for days of intense patient scanning. The data streams back across the 200 million miles to Earth, where scientists watch with bated breath. And what we find in these first examinations is staggering. Pixel's X-ray mapping reveals that the rocks are rich in olivine and pyroxene minerals, but they are laced with carbonates. On Earth, carbonates precipitate in liquid water and are exceptionally good at preserving fossilized life-forming structures like limestone and coral reefs. To find them here in the bedrock of a former lake is like finding a perfectly preserved library, even if we don't yet know if any of the books have writing inside. We see clear evidence that this rock was soaked in water, not once but multiple times, creating a stable, long-lived aquatic environment. Then comes the data from Sherlock. Across multiple scans in several different locations within these water-altered rocks, it registers a clear and persistent signal. A distinct fluorescence that can only come from one source, organic molecules. It is not life. We must be absolutely clear. These simple carbon compounds can be created by non-biological processes, but finding them here in this specific type of rock that was bathed in liquid water for millennia is a discovery of monumental significance. We have found the ingredients, we have found the kitchen, we have confirmed the recipe was possible. The building blocks for life as we know it were present in the waters of Jezero Crater. The environment was not just habitable in theory, it possessed the fundamental chemical components that life would have needed to arise. The question, the one that has driven us across the void to this very spot, no longer feels like a fantasy. It feels immediate, it feels urgent. After months of this meticulous survey, after mapping the chemistry and history written in the crater floor, the team now knows where to look. They have found the perfect geological time capsule, a single fine-grained mudstone part of an ancient shoreline rich in these carbonates and laced with the organic signatures Sherlock has sniffed out. It is a rock that has been waiting patiently, holding its breath for 3.5 billion years. It sits under the thin butterscotch sky, an unassuming piece of stone that may hold an answer that will redefine our place in the universe. All the reconnaissance is done, all the instruments have pointed the way, all the evidence suggests that if a secret is to be found in Jezero, it is likely to be found right here. The robotic arm moves once more, but this time it is not the abrader or the scanners that it brings forward. It is the drill, a hollow coring bit designed to extract a perfect finger-sized cylinder of rock, a pristine sample of the ancient Martian past. The time for looking is over. Now we must take the next step. We must reach into the heart of the stone itself. After months of traversing the broken ochre floor of the crater, Perseverance arrived. It was here at the foot of an ancient desiccated delta that the entire mission, and perhaps a fundamental question of our existence, reached its precipice. Before the rover lay not one but three distinct geological formations, each a tantalizing candidate, each whispering a different promise from a past drenched in water. The data that had guided us here, the orbital scans and the long-distance spectroscopy had done its job. It had led us to the promised land. But now standing at the border, we faced the oldest and most profound of dilemmas, the agony of choice. This was no longer about finding a habitable environment. The evidence for that was now overwhelming, written in every layer of sediment and sulfate vein. This was about something infinitely more specific, more consequential. It was about choosing the single solitary piece of Mars that would be enshrined, sealed, and one day sent home to tell its story. We had come seeking a ghost, and now we stood in a room full of them, forced to decide which one to ask for its name. The teams back on Earth, connected to this lonely outpost by a thread of radio waves, entered a crucible of debate, unlike any in the history of exploration. In the virtual rooms of the Jet Propulsion Laboratory, and in universities scattered across the globe, the world's finest minds became advocates, champions for a few kilograms of alien rock. The light delay, that agonizing minutes-long gap in conversation between Earth and Mars, seemed to stretch into an eternity, each second thick with the weight of the decision. On their screens were images of breathtaking clarity beamed from the rover's Mastcam Z and its Watson camera, showing textures and grains that no satellite could ever resolve. These were not abstract maps anymore. This was ground truth. This was the Earth-like mudstone, a contender codenamed Hargreaves after the pioneering geologist. Its fine, almost silty layers were the perfect medium in theory for entombing the delicate remains of microbial mats. It was the conservative choice the textbook placed to look. If life on Mars was anything like life on Earth, its most ancient traces would be found in a place just like this. The argument for Hargreaves was one of geological probability, a bet on the universal nature of biology. It was the quiet, confident whisper in the room. Then there was the maverick, the geological outlier the team had nicknamed K7, for its seventh and most startling potassium signature. It was a rugged crystalline outcrop, a chimera of minerals that had no simple explanation. Its surface was pockmarked with strange dark nodules rich in manganese and iron oxides. This was not the gentle environment of a placid lake bed. This was the chemical aftermath of something dynamic, perhaps an ancient hydrothermal vent, a place of intense energy. The spectral data from the Sherlock instrument, our laser-powered detective for organic molecules, lit up with ambiguous but persistent signals from K7. It was a scream, not a whisper. The risk was enormous. These signals could be nothing more than a mineralogical phantom, a complex abiotic chemistry that mimicked life leading us on a wild goose chase for decades. But if it was real, if these were indeed concentrated clusters of complex organics, K7 wasn't just evidence of life. It was a potential fossil of a Martian metabolism, a snapshot of life thriving on a chemical cocktail utterly alien to our own. To choose K7 was to gamble, to bet that Martian life was not just a familiar echo of Earth's, but something strange, something new. And finally, there was the third way, a formation of pale layered carbonates dubbed the archive. Carbonates form over vast timescales, precipitating out of standing bodies of water. Each layer is a page in a planetary history book. While not as fine-grained as the Hargreaves mudstone, nor as chemically dramatic as K7, the archive offered something unique, a chronology. If life existed in Jezrero's ancient lake, its chemical fingerprints could be trapped sequentially in these layers, telling us not just that life existed, but how it persisted through changing seasons and evolving climates. It was the safest bet for context. Drilling into the archive was like drilling into an ice core from Earth's own past. The sample might not hold a perfectly preserved cell, but it could contain an irrefutable chemical timeline of a biosphere. It was the historian's choice, a selection that prioritized the grand narrative over the single stunning discovery. The debate raged. Was it better to capture a potential fossil, a chemical anomaly, or a planetary history? Each choice meant abandoning the others, perhaps forever. The rover had a limited number of sample tubes. Each one was a vessel for a dream, and there were not enough to carry them all. The decision could not be made from orbit, nor from a distance of a few meters. To break the deadlock, Perseverance was commanded to reach out and touch these ancient stones. This is what it was built for. The arm, a 2-meter marvel of engineering, unfurled with balletic grace. At its tip, a turret of instruments spun into place a suite of sensors designed to give us a profound, intimate connection to this alien geology. First, the gas-puffing tool whisked away the modern Martian dust, the thin, corrosive blanket that conceals the past. We were for the first time seeing the true unweathered face of these rocks. The change was breathtaking. Colours shifted, textures emerged. The Hargraves mudstone revealed laminations so fine they looked like the pages of a book left out in the rain. The K7 outcrop showed a strange, almost greasy lustre within its dark nodules. The archive's carbonate layers became sharply defined a stark white and grey barcode of time itself. We were no longer looking at rocks. We were looking at characters in a 4-billion-year-old story, and we had to choose the protagonist. Then came the abrasion. A grinding bit on the rover's arm spun, creating a small circular patch of freshly exposed rock on each of the 3 targets. It was the geological equivalent of opening a sealed book. Now the most powerful instruments could get to work reading the pristine interior. PXL, the planetary instrument for X-ray lithochemistry, was brought to bear. Firing a hair-thin X-ray beam, it began to map the elemental composition of the abraded patches, pixel by pixel, with microscopic precision. Back on Earth, the science team watched breathless as these elemental maps materialized on their screens. They were works of abstract art, beautiful mosaics of color representing iron, silicon, calcium, and phosphorus. They were seeing the fundamental building blocks of this world arranged not by chance, but by the lost laws of Martian water and time. In the archive, the maps showed clear, distinct bands of calcium and magnesium confirming its origin in a stable lake. In the Hargraves mudstone, they saw clays rich in aluminum and silicon perfect for fossilization. But on K7, the maps were a riot. The dark nodules were shockingly concentrated in manganese surrounded by halos of silica and sulfates. It was a chemical disequilibrium, a signature that on Earth is almost exclusively mediated by microbial life. The needle was moving. But the final arbiter would be Sherlock. Its deep ultraviolet laser scanned across the abraded patches, causing any organic compounds to fluoresce to glow in the dark like ghosts. The data it sent back was not a simple picture, but a complex spectrum of light, a chemical fingerprint. And when Sherlock scanned the strange nodules on K7, it returned a spectrum that sent a shockwave through the mission. It showed the distinct signature of aromatic hydrocarbons, ring-like carbon molecules that are fundamental components of life as we know it. They are not in themselves proof of life. Such molecules can form through non-biological processes, but their concentration, their specific location inside these bizarre manganese-rich structures, and their association with an aqueous environment, it was a convergence of evidence that no one could ignore. The argument from K7 was no longer a scream. It was a coherent, compelling, and utterly chilling sentence. The debate subsided. The dissent grew quiet, replaced by a shared palpable sense of awe and terror. The gamble no longer seemed like a gamble. It seemed like destiny. The team had their consensus. They would drill K7. The command, encoded in a stream of ones and zeros, leaped across the void from Goldston, California. On Mars, Perseverance received its instructions and began the most delicate and important task it would ever perform. The massive rotary percussive drill on its arm whirred to life. There was no human hand to guide it, only the flawless pre-programmed will of its software honed by years of testing in simulated Martian landscapes on Earth. The hollow coring bit of tungsten carbide marvel pressed against the dark nodular surface of K7. For an agonizingly long period the world waited. The rover, a solitary machine representing the hopes of billions, carefully, meticulously drilled into the stone. The vibrations, the temperature, the torque, every parameter was monitored in real time, a mechanical meditation. It was not a violent act, but a surgical one. The goal was to extract a perfect finger-sized core of the rock, preserving its structure, its layers and its secrets completely intact. After 17 minutes that felt like a lifetime, the drill retracted. Inside the bit held by a small ingenious retaining ring was a cylinder of Mars, a piece of K7 that had not seen the light of day for more than 3.5 billion years. Now the sample had to be sealed for its impossible journey home. The rover's arm moved with the solemnity of a priest performing a rite. It manoeuvred the drill bit over to the sample handling assembly, a gleaming intricate mechanism at the front of the rover's chassis. Here inside the rover's belly, a complex dance of robotics began a process designed to be one of the cleanest operations in the solar system. The core was pushed from the bit and photographed from every angle, its dimensions assessed by lasers to ensure it was the right size. It was perfect. A pristine titanium sample tube, one of 43 that Perseverance carried from Earth, was manipulated into position. Each tube had been sterilized and baked for days at extreme temperatures, assembled in the cleanest room on our planet, engineered to be a perfect vessel, an impenetrable vault. It was a sterile steel womb waiting for its precious cargo. The core of K7 was carefully, gently guided inside. You could feel the collective exhalation of a planet as the internal cameras confirmed the transfer was successful. The final step was the most critical. A sealing cap was pressed into the tube and a hermetic seal was created, a weld of metal against metal, so perfect that not a single atom from the modern Martian atmosphere could get inside and nothing from inside could get out. The tube was now a time capsule. It was a message in a bottle thrown into the cosmic ocean, except this time we knew the exact coordinates of the shore it was destined for. Inside that small titanium cylinder, less than 15 grams of rock, now sat the most profound question ever asked. Is there life beyond Earth? That question was no longer an abstraction, no longer a philosophical musing. It now had weight. It had a serial number 266. It had a name. The rover's arm took the sealed tube, this potential Rosetta Stone of extraterrestrial life, and deposited it into its internal storage carousel where it clicked securely into place. It now lies in the darkness, waiting for the day when a future mission will arrive to retrieve it, to pluck this single extraordinary sample from the red dust, and begin the long, long journey home. The choice has been made. The first letter in a sentence that could rewrite everything we know about our place in the universe has been written, sealed and stored. The silence that follows is filled with a single deafening question: what happens next? And so they wait. Sealed in their titanium tubes lying in the ochre dust of Jezero crater, these slivers of another world have become the most precious objects in the solar system. Each one is a time capsule, a geological messenger, a potential Rosetta Stone for deciphering the greatest of all mysteries. They are a treasure beyond price, gathered at immense cost and with breathtaking ingenuity. But their collection was merely the first act in a cosmic drama of unprecedented scale. For all of Perseverance's triumphs, the rover is a field geologist, not a courier. It cannot bring its priceless discoveries home. Now a new challenge begins, a mission so complex, so audacious, it makes landing a car-sized robot on Mars seem like a preliminary exercise. The next great chapter in our exploration of the cosmos is not about going to Mars, but about coming back. This is the story of the Mars Sample Return, a multi-planetary, multi-generational celestial heist engineered to bring a piece of the red planet to Earth. It is a cosmic relay race across more than 100 million kilometers of unforgiving void, a chain of events where every single link must hold perfectly. The stakes are not just scientific, they are existential. We are about to attempt to retrieve a message in a bottle thrown from a distant shore, a message that might just tell us we are not alone. The first step in this monumental journey requires us to return to the world we just explored, but this time with a very different purpose. The curtain rises on the first actor in this new play, the sample retrieval lander. Imagine a machine larger and more massive than Perseverance beginning its own fiery descent through the thin Martian air. This isn't a rover designed for years of wandering exploration. It is a dedicated logistics hub, a stationary base of operations for the most critical handoff in history. Its landing must be impossibly precise, touching down within a few hundred meters of the sample depot Perseverance so carefully established a location now known as Three Forks. This landing itself is a moment of supreme tension. A mistake of a few kilometers would render the entire subsequent chain of events impossible. The lander must become a steadfast anchor in the shifting sands, the starting block for the next leg of this extraordinary relay. Once it has confirmed its stability, its cargo bay will open to reveal two key passengers. One is a rocket poised to make history. The other is a new kind of rover, a marvel of minimalist engineering designed for a single high-stakes purpose. It is the Fetch rover, and its job is to perform a series of meticulous retrievals that will echo for centuries. This rover is not a slow methodical geologist like its larger cousin. It is an agile courier built for speed and precision. Smaller, lighter, and equipped with wheels designed for rapid traverses across the crater floor, it is a robotic bloodhound tasked with hunting down the samples one by one. Its primary tool is not a drill or a spectrometer, but a sophisticated grapple, a robotic arm of exquisite dexterity. As it rolls out onto the Martian surface, its world is defined by a single imperative: find the tubes. Guided by the precise location data logged by Perseverance, the Fetch rover will navigate to each sample location. You have to picture the scene. A small frantic machine, a stark piece of terrestrial technology zipping across a silent alien landscape that has remained undisturbed for eons. It approaches the first gleaming cylinder, a tiny beacon of human ambition against the rust-coloured panorama. Now the real test of its design begins. The arm extends its gripper, aligning with the unique contours of the sample tube. The digital brain of the rover must account for the angle of the tube, the texture of the soil it rests upon, and the subtle play of Martian gravity. The grip must be firm enough to secure its prize, yet gentle enough to avoid any damage. For a few silent, agonizing moments, the rover performs its delicate surgery, plucking the sample from the dust where it has lain in wait. The tube is then carefully lifted and secured into a storage rack on the rover's body. Then it moves on to the next. One by one, it must gather the entire collection, a metallic harvest from a barren field. The process will be repeated dozens of times, a slow, methodical, and nerve-wracking accumulation of cosmic treasure. But what if something goes wrong? What if a tube is lodged in a way the gripper cannot manage? What if the Fetch rover itself suffers a mechanical failure? A wheel stuck in a sand trap, its mission cut short millions of kilometers from the nearest mechanic. The architects of this mission have planned for such a contingency. In a remarkable display of foresight, Perseverance itself serves as the ultimate backup plan. If the Fetch rover falters, the grand old explorer of Jezero Crater would be called upon to perform one final heroic duty. It would abandon its own scientific investigations and embark on a journey to its own sample depot, retrieving the duplicate set of tubes it has kept safe within its own chassis. It would then have to drive slowly and carefully across the crater to the sample retrieval lander and deliver its precious cargo directly. This is Plan B, a scenario everyone hopes to avoid, yet one for which we must be prepared. It transforms Perseverance from a pioneer into a guardian, the final guarantor that our investment in this world will not be lost. Assuming the Fetch rover succeeds, however, it will return to the lander, its rack filled with the future of planetary science. It will align itself perfectly with the lander's deck, and its robotic arm will begin the next critical transfer, placing each tube one by one into the payload capsule of the second passenger it brought to Mars, the Mars Ascent Vehicle. Here we stand on the precipice of a truly historic moment, an achievement that will redefine our relationship with the solar system. For the first time in history, humanity is about to launch a rocket from the surface of another planet. This is the Mars Ascent Vehicle, or MAV, a compact two-stage solid fuel rocket that represents a quantum leap in our capabilities. It is in essence a missile aimed at the sky, but its target is not an enemy. It is a specific razor-thin corridor of space in low Mars orbit. Every aspect of its design has been dictated by the brutal realities of the Martian environment. Its solid rocket motors are formulated to ignite and burn reliably, in temperatures that can plummet to more than 100 degrees below 0 Celsius. Firing a rocket on Earth is a well-understood science, a dance of chemistry and physics in a thick, forgiving atmosphere. On Mars, the atmosphere is less than 1% as dense as Earth's. This presents a unique aerodynamic challenge. The rocket will scream upwards with very little air to push against, making its guidance and control systems work overtime to maintain a stable trajectory. The launch is a moment of pure, unadulterated power. With the sample capsule securely loaded and sealed, a tiny canister, now containing the hopes of a generation of scientists the MAV will ignite. It will blast off from the deck of the lander a pillar of fire and fury against the pale pink sky, a violent, beautiful intrusion into the planet's ancient tranquility. For a few breathtaking minutes, it will be the fastest, most powerful object on Mars, accelerating at a ferocious rate to escape the planet's gravitational grip. It must not only achieve escape velocity, but do so with surgical precision, delivering its payload to an orbital altitude of roughly 380 kilometers. It is aiming for a moving target and orbital rendezvous point, where another much larger spacecraft will be waiting. As the MAV ascends, its first stage will burn out and be jettisoned, crashing back to the Martian surface. The second stage will then ignite a final powerful kick to push the sample container into a stable, predictable orbit. Once the correct altitude and velocity are achieved, the second stage will perform its last act. A spring-loaded mechanism will deploy gently, pushing the sample container away from the spent rocket motor. The container, now officially designated the orbiting sample or OS, is on its own. It is a gleaming basketball-sized sphere tumbling slowly in the blackness of space above the crimson curve of Mars. It is utterly alone, a silent metallic satellite carrying an extraordinary secret. It is now a beacon broadcasting a simple signal waiting to be found. Its journey is far from over. It has merely completed the second leg of the relay. The baton now in orbit must be passed to the next runner, a sentinel that has been patiently circling the red planet waiting for this very moment. That sentinel is the Earth Return Orbiter, or ERO, a titan of a spacecraft built by the European Space Agency. It is the largest spacecraft ever sent to Mars, a behemoth, powered by vast solar arrays that span nearly 40 meters, giving it the appearance of a colossal dragonfly. For months it has been using a hyper-efficient ion engine, a gentle but relentless thruster, that sips xenon gas to carefully shape and refine its orbit around Mars. Its mission to find and capture the tiny orbiting sample. This is not a simple task. It is an autonomous high-speed chase and rendezvous, millions of kilometers from any human control. The light-speed delay between Earth and Mars makes real-time piloting impossible. The ERO must perform this cosmic ballet all by itself. Using its own suite of cameras and tracking sensors, the ERO will begin its hunt. It will detect the OS first as a faint star-like point of light, then gradually resolving it into a definite object. The orbiter's onboard computers will perform a complex series of orbital calculations, firing its thrusters in precise bursts to match the speed and trajectory of its target. The final approach is a slow, methodical process, a delicate dance of gravitational mechanics. The ERO will close the distance over a period of days, cautiously moving closer until it is just meters away from the OS. At this point, the true ingenuity of the capture system is revealed. The ERO is equipped with a capture containment and return system, a sophisticated robotic mouth designed to swallow the OS whole. As the two spacecraft fly in perfect formation, the doors to this system will open. The ERO will then move forward, gently enveloping the OS within its capture cone. Once inside, sensors will confirm its position, and a lid will close, securing the sample container. But this is more than a simple capture. It is the beginning of a critical process of biocontainment, a protocol known as breaking the chain of contact. We are operating under the assumption, however remote, that the samples might contain Martian life. Therefore, no part of any hardware that has ever touched the surface of Mars can be allowed to return to Earth's biosphere. The OS, having been launched from the surface, is considered contaminated. Inside the ERO's containment system, a series of robotic arms will get to work. They will manipulate the orbiting sample, placing it inside another larger vessel. This outer vessel is then sealed with a process of high-temperature brazing, creating a perfect hermetic weld. This containment within a containment strategy ensures that the Martian material is completely isolated. The ERO's capture mechanism, the part that physically touched the OS, is then sealed off, never to be exposed to the rest of the spacecraft. The chain is broken. The pristine sealed container now holds the samples protected and ready for the long voyage home. With its precious cargo secured, the Earth Return Orbiter will fire its main ion engines once more. It will spend months slowly spiraling away from Mars, building up the velocity needed to break free of the planet's gravity and begin the interplanetary transit back to Earth. This is the longest and quietest part of the journey. For close to a year, the spacecraft will coast through the vacuum, a silent arc carrying the first physical pieces of another world destined for human hands. Its journey is a testament to the power of celestial mechanics, a carefully plotted trajectory that uses the gravitational pull of the Sun to guide it home. As it nears our planet, the final and perhaps most perilous phase of the entire mission begins. The ERO will not attempt to enter Earth's orbit or land. It is too large and it has spent too much time in deep space. More importantly, it is a piece of hardware that has orbited Mars and is therefore, by the strict rules of planetary protection, considered potentially contaminated. Its job is to be a cosmic catapult. As it approaches Earth, it will align itself with pinpoint accuracy. The containment vessel now housed within a specialized landing craft, called the Earth Entry Vehicle, will be released. This is the final handoff. The ERO will then fire its thrusters one last time, deflecting its own course to fly past our planet and enter a permanent stable orbit around the Sun, its historic mission complete. The Earth Entry Vehicle, or EEV, is now alone on a direct collision course with Earth. It is a passive vessel, a marvel of simplicity designed to do one thing: survive. It has no engine, no navigation system, no parachutes in the conventional sense. It is essentially a heat shield, a flying, saucer-shaped aeroshell designed to withstand the hellish temperatures of atmospheric re-entry. It will slam into Earth's upper atmosphere at a staggering velocity of over 40,000 kilometers per hour. For a few terrifying minutes, it will become a man-made meteor, a searing fireball streaking across the sky. The friction will generate temperatures hotter than the surface of the Sun, yet the precious samples inside, protected by layers of advanced thermal insulation, will remain cool and stable. The angle of its entry is absolutely critical. Too steep, and it will burn up completely. Too shallow, and it will skip off the atmosphere like a stone on a pond lost forever to space. It must hit a gravitational keyhole just a few kilometers wide. This is a controlled fall of the highest order. The EV is designed to be aerodynamically stable, using its shape to slow itself down as the atmosphere thickens. After bleeding off the vast majority of its cosmic velocity, when it has descended to a designated altitude, a small drogue parachute will deploy, followed by a main parachute. These will not bring it to a gentle landing. They are designed only to orient the vehicle and ensure it impacts the ground at a predictable, albeit high, speed. It is a hard landing, a controlled crash into the desolate pre-selected sands of the Utah Test and Training Range. The vehicle itself is built to crumple and absorb the impact, protecting the robust triple-sealed container at its heart. And then, silence. A cloud of dust settles under the desert sun. Somewhere in that vast empty landscape lies a small scorched capsule, the endpoint of a decade-long multi-billion-dollar interplanetary odyssey. A beacon will activate, transmitting its location to recovery teams standing by, who will scramble in helicopters to retrieve it. This small piece of hardware now sitting on Earth represents the culmination of one of the most ambitious technological undertakings in human history. It is a vessel containing not just rock and dust, but the potential for a revolution in our understanding of the universe and our place within it. The journey is over, but the true adventure, the quest to unlock the secrets sealed within, is only just beginning. Its long journey across the void had finally ended. The container, a marvel of engineering forged to survive the fury of atmospheric entry, and the unforgiving chill of deep space, now rested within the most sterile place on Earth. This was not merely a laboratory. It was a sanctuary, a cosmic quarantine designed with a singular paradoxical purpose: to protect Earth from Mars and to protect Mars from us. Located deep underground, shielded by meters of reinforced concrete, the facility hums with a silent, invisible energy. Here the air itself is a carefully curated artifact, scrubbed and filtered to a purity that exists nowhere in nature, exchanged 10 times a minute to whisk away any stray terrestrial mote. The pressure is kept deliberately unnervingly low, an invisible gravitational well, ensuring that if a breach ever occurred, air would rush in, not out. Nothing from Mars would ever escape. This is the inner sanctum of the Planetary Protection Protocol, the final airlock of history through which this precious and potentially perilous cargo must pass. You are watching it now through layers of radiation-hardened glass, your perspective shared with the handful of scientists whose life's work has led them to this very moment, Their faces a mixture of awe and trepidation. They don't breathe the air in the chamber. They don't touch the surfaces. Their role is that of silent, anxious observers, gods of this sterile universe watching their creations do the work. Inside, under the glare of shadowless antiseptic light, a ballet of chrome and steel begins. Robotic arms more precise and steady than any human hand awaken from their slumber. Their movements are impossibly smooth, deliberate and slow, each motion pre-programmed and rehearsed 1,000 times with identical mock-ups. There can be no mistakes here. No fumbled grips, no accidental drops, no catastrophic errors. The stakes are simply too high. One arm equipped with a delicate but powerful gripping claw approaches the main transport vessel. Another extends a laser, its invisible beam scanning the container's surface, mapping every microscopic feature, every speck of Martian dust that still clings to its exterior from the plains of Jezero crater. This outer layer, the contact analog material, is meticulously ablated, vaporized atom by atom, and siphoned away for a separate analysis. Only then, once the vessel has been stripped of its journey, can the work of opening it truly begin. We have followed this sample from the moment Perseverance drilled it, a ghost of a vibration on a world 200 million kilometers away. We have traced its path as it was cached collected, and launched a lonely courier carrying a secret 4 billion years in the making. Now the final seal is about to be broken. The primary titanium tube, the one we have seen in countless simulations, is carefully extracted from its protective cocoon. It glints under the sterile lights, a simple cylinder that has become the most valuable object on the planet. A specialized robotic tool latches onto one end, another secures the body of the tube. There is a collective intake of breath in the control room, a sound that seems deafening in the otherwise silent chamber. Then, with infinitesimal slowness, the cap begins to turn. The fine threads machined to tolerances of a single micron disengage with a precision that is utterly silent. No pop, no hiss of escaping atmosphere. The Martian air, thin and cold, was captured along with the sample, and the first instrument to greet it is a mass spectrometer, a sensitive artificial nose that sniffs this ancient air. It tastes the argon, the carbon dioxide, the trace nitrogen, confirming the purity of the sample, a final system check before the great reveal. The data streams onto a monitor in the observation room. The isotopic ratios are perfectly Martian. The seal held. The sample is pristine. A wave of quiet relief washes over the assembled team. The first and perhaps most fraught hurdle has been cleared. Now the inner contents can be revealed. The robotic arm gently tips the tube, and with a movement so delicate it seems to be defying gravity, a core of dull, reddish-brown rock slides out onto a sterile black obsidian tray. There it is. For the first time, a piece of Mars chosen for its unique promise sits exposed in an earthly environment. It looks unassuming. Just a rock. Small, barely 5 centimeters long, layered with subtle bands of grey, and a rusty ochre that speaks of eons of oxidation. Yet to the geologist watching it is a masterpiece. A page torn from the red planet's primordial diary. But it is not the rock itself that is the primary target. It is what's within. Specifically that strange greenish vein-like structure, first identified by the rover's Sherlock instrument, the feature that hinted at a long-ago interaction with water and perhaps something more. The initial examination is purely optical, a reconnaissance mission. A suite of high-resolution cameras and microscopes swivels into position, their lenses gazing down like alien eyes. They zoom in closer and closer, resolving features far beyond what Perseverance could ever have managed. The image that appears on the main screen is breathtaking. Under magnification, the boundary between the dull red rock and the greenish vein is not a simple line, but a complex fractal shoreline between two different chemical realities. Within the greenish material, which we now see as more of a complex carbonate, are tiny dark spherical and filamentous inclusions. They are microscopic, smaller than a grain of terrestrial sand, but their shapes are evocative. They are not the sharp, crystalline geometries of pure mineralogy. They are curved. They are segmented. They seem to cluster together in chains and mats hauntingly reminiscent of the microbial colonies we find fossilized in the most ancient rocks on our own planet. A hushed whisper ripples through the control room. Is it possible? could we be looking at the fossilized remains of Martian microbes? The shapes are compelling, deeply suggestive, but morphology alone is never proof. Nature is a clever mimic, and abiotic processes can create deceptively biological-looking structures. The team knows this. They hold their emotions in check. The real interrogation is about to begin. The next phase moves beyond what things look like and into the far more profound question of what they are made of. A robotic arm, this one armed with a diamond-tipped microsaw, excises a sliver of the sample from the vein, a section no thicker than a human hair. This tiny fragment is then delivered to the first of many instruments that will probe its fundamental nature. It begins with a laser, Raman spectroscopy. A focused beam of monochromatic light bathes the microsample, exciting its molecules, causing them to vibrate and scatter the light. Most of the light scatters back unchanged, but a tiny fraction, just one photon in a million shifts in energy, a change that is unique to the chemical bonds that produced it. It is a way of reading a molecule's fingerprint from a distance. The scattered light is collected, its spectrum analysed. The first results flash on the screen. The computer decodes the spectral shifts, translating them into chemical identities. Water bound up in the mineral matrix, confirmed. Carbonates, confirmed. Iron oxides, confirmed. And then, something else. A complex series of peaks appears in a very specific part of the spectrum, a pattern that the analysis software flags immediately. The signature is unmistakable. It is the telltale sign of complex organic molecules. Not just simple methane or formaldehyde, which can form naturally, but long-chain hydrocarbons, polycyclic aromatic hydrocarbons, and other carbon-based structures with a complexity that on Earth is almost exclusively the domain of biology. A palpable tension fills the air. This is the signal Perseverance had hinted at, but here in the controlled environment of the lab, the signal is 10,000 times stronger, clearer, undeniable. The rock contains the building blocks of life. But even this is not the final word. Complex organics have been found in meteorites before, formed in the cold, sterile chemistry of interstellar space. The team needs more. They need to know if this carbon was organized by a living process. The second sample sliver is prepared. This time it is destined for a machine that will utterly destroy it, but in that destruction find the ultimate truth. It is placed into a gas chromatograph mass spectrometer, a device that first vaporizes the sample at extreme temperatures, then sends the resulting gas through a long coiled tube. Different molecules travel through the tube at different speeds, separating them out like runners in a race. As each molecule emerges, it is blasted with an electron beam, shattering it into charged fragments. A powerful magnet then weighs each fragment with incredible precision. From this chemical carnage, a complete inventory of the sample's organic composition can be reconstructed. For hours, the machine works its silent, methodical magic. The scientists wait, watching the complex data cascade down their screens. They are looking for something very specific. They are hunting for a bias. Life as we know it is picky. When it builds its molecules, like the lipids that form cell walls, it tends to construct them with an even number of carbon atoms. Non-biological chemistry has no such preference. It produces a random assortment of both even and odd-numbered chains. The hours crawl by, the tension mounting with every data point processed. Then the graph begins to take shape. A histogram showing the distribution of lipid chain lengths, a low peak at 9 carbon atoms, a massive peak at 10, a low peak at 11, a massive peak at 12. 13 is low, 14 is high, 15 is low, 16 is high. The pattern is stark, rhythmic, and utterly unambiguous. A powerful, undeniable preference for even-numbered carbon chains. It's a pattern that screams biology. It is a ghost of a metabolism, an echo of a cellular machine that once assembled these fats for its own purposes. One of the senior scientists, a woman who has dedicated 40 years to the search for extraterrestrial life, slowly removes her glasses and rubs her eyes as if she can't believe what the data is telling her. Her voice when she speaks is barely a whisper. Look at the distribution. It's a biological preference. It has to be. But there is one final test. The one that can, for the first time in human history, potentially deliver the knockout blow. The analysis of carbon isotopes. Carbon in the universe comes in 2 main stable forms, the common lighter, carbon-12, and the rarer, heavier carbon-13. Geological and chemical processes are largely indifferent to this slight difference in weight. But life is lazy. It finds it metabolically easier to process the lighter carbon-12 atom. Over time, any biological material becomes noticeably enriched in the lighter isotope, while the surrounding environment is left with a higher proportion of the heavier one. This isotopic signature is one of the most robust and trusted biomarkers we have. It is the final question you ask of a sample when you want to know once and for all if life was involved. A third microsample, the last of the initial batch, is prepared for the isotope ratio mass spectrometer. This is the moment of truth, the culmination of a multi-decade, multi-billion-dollar effort, the fulfillment of a dream that began the first time a human ever looked at Mars and wondered, are we alone? The machine requires time to achieve a perfect vacuum and calibrate. The wait is agonizing. No one speaks. The only sound is the quiet hum of the air circulation systems and the frantic, silent beating of hearts in the observation room. The machine ingests the sample. The numbers begin to populate the screen. The ratio of carbon-13 to carbon-12 from the surrounding rock matrix is calculated, first establishing the Martian baseline. It is, as expected, consistent with other known Martian meteorites. Then the instrument begins to analyze the carbon extracted purely from the complex organic molecules within the vein. The seconds stretch into an eternity. The computer churns through the complex calculations, cross-referencing, verifying, eliminating any potential for error. And then the final value appears, a single number displayed in stark white digits against a black background. There is a long, breathless silence. The number is not just slightly different from the baseline, it is profoundly, shockingly different. The depletion of the heavier carbon-13 isotope is massive, far beyond any known abiotic process. It is a signature so strong, so clear that on Earth it would be considered incontrovertible proof of ancient biological activity. The three lines of evidence have converged. The microfossil-like structures with their hauntingly biological shapes. The organic molecules with their clear preference for even-numbered chains. And now this, the isotopic fingerprint, the final silent symphony of atoms that can only be explained by the metabolic processes of life. No one cheers, no one celebrates. The sheer, crushing weight of the discovery descends upon the room. It is a moment not of triumph, but of profound, earth-shattering revelation. The scientists stare at the screen, then at each other. They have just become the first human beings to know with near certainty that we are not alone in the universe, that life is not a miracle unique to this world, but a cosmic imperative that once took hold on our nearest neighbour. The rock from Mars is not just a rock, it is a tombstone, it is a messenger, it is a Rosetta Stone for a second Genesis. A chill runs through you as you watch their stunned faces because you understand what this moment truly means. Everything has changed. Our place in the cosmos, the story of our own origins, the future of our species, it has all been irrevocably altered by this one small piece of another world. The scientific community does not yet know. The world does not yet know. But in this silent, sterile room, buried deep beneath the ground, a new chapter of human history has just been written, and the shockwaves from this single discovery are about to ripple outwards to shake the very foundations of everything we thought we knew about our universe and about ourselves. And so the wait is over. The silence that has defined our search for cosmic companionship, a profound and lonely quiet stretching across generations of stargazers, has finally been answered. Not with the triumphant fanfare of a radio signal from a distant star, nor with the arrival of a vessel from beyond the sun. It came as a whisper, a fossilized secret held in a fragment of stone, a microscopic testament delivered from our nearest celestial neighbour. The data streams have been triple-checked, the results peer-reviewed, the arguments and counter-arguments exhausted in sterile laboratories. The conclusion, however improbable, however reality-altering, is inescapable. The rust-coloured dust of Mars once felt the pulse of life. That single, unassailable fact now hangs in our collective consciousness, a new star in our intellectual sky, and everything from this moment on is different. We stand on a precipice we have only ever dreamed of, looking out not at an empty universe, but at a cosmos that has revealed a hint, just a hint of its true biological richness. The great monologue of humanity, our long soliloquy about meaning and purpose, has been interrupted by a voice from another world. And though it speaks a language of biochemistry and ancient geology, we understand its core message perfectly: we're not alone. This confirmation does not close a book. It opens a library of astonishing and perhaps terrifying new questions that cut to the very core of our existence. Before us lie two doors, two possible realities, each one more profound than the last. Behind the first door is a universe where life is a tenacious traveller. This is the world of panspermia, the hypothesis that life once started can be ferried between worlds on the wreckage of planetary collisions. In this scenario, the Martian microbes and the life teeming on Earth are not strangers, but distant cousins sharing a common ancestor. They would be two branches of the same family tree seeded from a single origin, perhaps here on Earth, perhaps on a warmer, wetter, ancient Mars, or perhaps from somewhere else entirely long before our sun even ignited. This would mean that the solar system itself is a single interconnected biosphere. It would make us Martians and Martians us. Our worlds, separated by a gulf of cold vacuum, would be linked by an ancient unbroken chain of biology, a shared heritage written in DNA or something like it. It's a beautiful romantic notion, a story of cosmic kinship. Yet it also carries a subtle, chilling implication. If life from a single Genesis event struggled to take hold on just two adjacent rocks, two worlds in the same habitable zone, then life itself, its initial spark might be an exceptionally rare, perhaps singular event in the cosmos. We would have found a sibling, yes, but we might also have confirmed that our solar system is a lonely, isolated oasis of biology in a galaxy that remains overwhelmingly and perhaps eternally barren. The silence of the universe would not be an illusion. It would be the prevailing deafening truth. But then there is the second door. And to contemplate what lies behind it is to challenge the very foundations of what we believe to be possible. Behind this door is a universe where life is not a fluke. It is a feature. This is the world of a second Genesis, a reality where the breathtakingly complex transition from inert chemistry to biology is not a one-time miracle, but a natural, repeatable outcome of planetary evolution. It suggests that under the right conditions with the right ingredients, liquid water, a stable energy source, organic compounds, life is an emergent property of the universe itself. It would mean that the unthinking laws of physics and chemistry, when left to their own devices on a rocky world for 1 billion years, are biased toward creating biology. Think of what this signifies. If it happened here on our own planet, a world perfectly suited for us, and it also happened next door on a world that we see as a frozen, irradiated desert, a world that ultimately failed to sustain it, then what does that say about the countless worlds beyond the probability shifts from impossibly small to inevitably large? The Drake equation, once a theoretical exercise in speculation, gains a hard empirical variable that sends its solution soaring. A second Genesis in our own solar system implies that that all galaxies are not silent voids but are humming with life. It suggests that every stable star with a rocky planet in its habitable zone is a potential petri dish for biology. The cosmos in this view is seeded not with life itself, but with the promise of life. It is a fundamental cosmic imperative woven into the fabric of space-time. We would be forced to conclude that we are not the protagonists of the cosmic story, but merely one voice in a vast galactic choir that has been singing for eons. The rock in our laboratory is no longer just a sample. It becomes a key, a coded message from the universe itself telling us, what happened on your world is not special. It is the way of things. This is the choice that now confronts us, the grandest scientific question ever posed. Are we an echo of a single biological shout, or are we one of many voices? The answer will determine the entire future of our species' cosmic journey. And as we grapple with these immense scientific possibilities, we're forced to turn the lens back upon ourselves to confront the philosophical and ethical tempest this discovery unleashes. For millennia, our philosophies, our religions, our cultures have been built upon the bedrock of human exceptionalism. We have defined ourselves by our uniqueness, our consciousness, our art, our ability to question our own existence. We saw ourselves as the universe made self-aware, the soul bearers of the cosmic flame. How does that identity survive the knowledge that biology is common? The discovery of even a fossilized Martian microbe is a profound decentering event, a continuation of the Copernican revolution that moved us from the center of the universe and the Darwinian revolution that connected us to the animal kingdom. This is the next great humbling. It positions humanity not as the point of creation but as a participant. It does not diminish our art or our love or our capacity for wonder. Instead, it places them in a context of unimaginable scale. Our achievements become not a solitary miracle but our unique contribution to a universe far more creative and alive than we ever dared to imagine. It challenges us to find a new, more mature definition of our own significance, one based not on being alone but on being a part of something magnificent. This philosophical shift brings with it an urgent and profound ethical burden. Mars is no longer a dead rock, a destination for flags and footprints, a backup drive for humanity, a source of minerals to be mined. It is now and forever will be the site of a second biosphere. Even if that life is dormant, even if it is only a chemical fossil, the planet itself must be treated as a sacred ground, an archaeological site of unparalleled importance. We humanity are now the custodians of the only other example of life we know. This places an almost unbearable weight of responsibility upon our shoulders. Every mission we plan, every rover we land, every human footstep we contemplate must now be weighed against the risk of what scientists call forward contamination. The catastrophic possibility that we could introduce our own hardy terrestrial microbes to the Martian environment, microbes that could outcompete, overwhelm, and ultimately erase the subtle, ancient and alien biology that remains. We could become in our ignorance and haste the exterminators of an entire world's life, the destroyers of the very thing we sought to find. The irony is as tragic as it is profound. The prime directive of science fiction has crashed into the hard reality of science fact. What right do we have to explore? Do we drill deep into the Martian crust seeking extant life, knowing that our very drill bit could be a weapon of mass extinction? Do we establish colonies, terraform the planet, and bend it to our will, knowing that in doing so, we might be silencing the universe's only other local voice? These are no longer abstract debates for late-night student forums. They are now urgent policy questions for governments, for space agencies, and for every citizen of a species that is about to step out into its own solar system. We have a chilling history of exploration on our own planet, a legacy of disrupting and destroying ecosystems we did not understand. The great challenge for our generation and all that follow will be to prove that we have learned from that history that we can explore with wisdom and reverence, not just with power and ambition. Mars has become the ultimate test of our species' ethical maturity. The ripples of this discovery will not be confined to laboratories and mission control centres. They will wash over every aspect of our society, reshaping our world in ways we can only begin to predict. It could become the great unifier, the ultimate rallying cry for a fractured humanity. The knowledge that we share our solar system with another form of life could render our terrestrial squabbles, our national borders, our petty conflicts as absurdly insignificant as they truly are. It could galvanize a new era of global cooperation, a shared endeavor to explore the red planet, to pool our resources, our knowledge, and our spirit of discovery in a project that belongs to all humankind. A new space race could ignite, but one driven not by Cold War paranoia, but by a shared noble competition to unlock the secrets of this second genesis. It could inspire a renaissance in science and education, as a new generation looks up at that faint red light in the night sky, and sees not a symbol of a god of war, but a world of biological possibility, a tangible destination for their dreams and ambitions. But there is a darker path as well. Newfound knowledge has always been a source of power, and power is always coveted. Will the secrets of Martian biology become another resource to be fought over? Will nations race to Mars, not for science, but to claim its biological heritage, to patent its unique biochemistry, for unimaginable technological or medical gain? The discovery could deepen existing rivalries, creating a new and dangerous arena for geopolitical competition. The question of who owns Mars and the life that may still cling to existence there will become one of the most contentious legal and political issues of the 21st century. The societal impact will be a mirror reflecting back at us the best and worst of our own nature. This single rock, this fragment from another world, does more than tell us about life on Mars. It forces us to decide once and for all what kind of species we truly want to be. Regardless of the path we choose, one thing is certain: the quest has just begun. This discovery is not an endpoint. It is the firing of a starting pistol. The field of astrobiology, once a fringe discipline operating on the edge of speculation, is now at the very centre of human scientific endeavour. The search for life is no longer a question of if, but of where and how. The blueprints for our future in space will be redrawn from scratch. Missions will be designed with a new and ferocious urgency. We will send flotillas of new orbiters and landers. We will deploy drills capable of plunging kilometres beneath the Martian surface down into the deep warm aquifers where water might still flow and where Martian life may have retreated to make its last stand. Our gaze will turn with renewed purpose to the other promising worlds of our solar system, to the saltwater ocean hidden beneath the icy shell of Jupiter's moon Europa, to the geysers of Enceladus spewing the contents of a subterranean sea into space, offering tantalizing samples for any passing probe, to the methane lakes and thick nitrogen atmosphere of Titan, where a form of life unimaginably different from our own might be thriving. These are no longer just points of interest. They are now chapters in a cosmic detective story, and we have just found the first critical clue. The search for life will become the defining scientific adventure of this millennium, a multi-generational quest that will pull us further and further out into the cosmos. And what of us? What of the human journey? The call to send astronauts to Mars to walk upon its surface is now more than a matter of exploration. It is a scientific and philosophical imperative. To study Martian life in situ, to understand its habitat, its biochemistry, its evolutionary history, will require the one thing no robot can yet replicate: the creative, intuitive, and brilliant mind of a human scientist on the ground. The day is coming when a human being will stand on the red soil of Mars looking back at a tiny pale blue dot hanging in the black sky, and they will know with absolute certainty that they are not a visitor to a dead world, but an emissary from one living world to another. In that moment, the true significance of this journey will be realized. The small grey rock that travelled 100 million miles in a sterile container has done more than answer a question. It has given us a new story, a new and far grander narrative for ourselves. We are the generation that lifted a veil. We are the species that discovered a second Genesis next door. We have found that the universe is not a sterile collection of atoms and energy, but something far more mysterious, more complex, and more magnificent. It is a place that creates life, a cosmos that strives for awareness. The sample from Perseverance is our Rosetta Stone, the key we will use to begin translating the language of life in the universe. It has irrevocably and wonderfully altered our place within the cosmos, transforming us from cosmic orphans into members of a potentially vast and unseen biological family. Our work is not finished. In fact, it has just begun. We have heard a single, fossilized note from the cosmic symphony. Now, with a renewed sense of wonder, with a profound sense of responsibility, and with the unshakable knowledge that there is something out there to find, we must commit ourselves to listening with all our heart for the rest of the orchestra. The age of cosmic loneliness is over. The age of cosmic self-discovery has dawned.